Hello friends, welcome you all to the 21st lecture on function analysis and its applications. In this lecture, we will discuss the further theorems on finite-dimensional normed linear spaces. These are the contents of today's lecture, further theorems on finite-dimensional normed linear spaces. Proposition: if n is a finite-dimensional normed linear space, then n is complete, or any finite dimensional normed linear space is a Banach space. Proof: let dimension of n is n, where n greater than 0, and let x1, x2 and so on xn be a basis for n. In view of the theorem of lecture 20, it suffices to prove the completeness of n with respect to the zeroth norm for any x belonging to n. There exist unique scalars alpha 1, alpha 2 and so on alpha n defined by norm x, that is zeroth norm of x is equal to maximum of modulus of alpha I is equal to 1 to n, where x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. This can be written as summation I is equal to 1 to n alpha I xi is any vector in n. Let yi be any Cauchy sequence in n. Consider the ith term of this sequence. We have yi equal to alpha I1 x1 plus alpha I2 x2 plus and so on alpha in xn. Okay. Here yi is Cauchy sequence in n. Any vector of n, suppose x is belonging to n, then x is expressed as alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. So here yi be a Cauchy sequence in n, then yi also can be expressed as such type. For some uniquely determined scalars alpha I1, alpha I2 and so on alpha in. Since yi is a Cauchy sequence, we have norm yi minus ys at zeroth norm tend to 0 as is tend to infinity. But norm yi minus ys at zeroth norm equal to max of the modulus of alpha I k minus alpha s k. Okay. Why? Because zeroth norm defined this. So here yi minus ys as vector. So this can be written as alpha I k minus alpha s k. Okay. So as per the definition of zeroth norm, which by equation 1 implies that this is tend to 0 as is tend to infinity for k is equal to 1 to and so on n. Since ak either belong to R or C, set of all real number or set of complex number, each of which is complete. R or C, we know that complete space, there must exist scalar alpha 1, alpha 2 and so on alpha n such that alpha I k tend to alpha k, suppose here. Maximum of mod alpha I k minus alpha s k tend to 0, because this tend to 0, that is this tend to 0. This is the maximum value of this tend to 0, it means any alpha ik minus alpha sk tend to 0. Here alpha ik and alpha sk as scalar. Okay, so this indicates that Cauchy sequence in RRC. Okay, so Cauchy sequence in RRC, we know that R and C is a complete space. So any sequence alpha ik converges to alpha k as I tend to infinity. Let y is equal to summation k equal to 1 to n alpha k xk. Then yi converges to y, where y is this one. Y belonging to n. So we know that any vector x belonging to n, then it can be expressed as this one. So here y is the element of n, so y can be expressed summation k is equal to 1 to n alpha k xk. Okay, so here yi converges to y and y belonging to n. Hence n is complete. This completes the proof of theorem. Next theorem. If n is normed linear space and M is any finite dimensional subspace of n, then M is closed. Okay. By the above proposition, M is complete since every complete subspace of non-linear space n is closed. Therefore, M is closed. Already we have proved here. If n is a finite dimensional non-linear space, then n is complete. Okay. So by this proposition, here, if n is non-linear space and M is finite dimensional subspace of n. So by above proposition, M is complete. Since every complete subspace of non-linear space, n is closed. Therefore, M is closed. Next theorem. If n is finite dimensional normed linear space and n dash any arbitrary normed linear space, then every linear transformation T of n into n dash is continuous. Proof. Let the dimension of n be n and let x1, x2 and so on xn be basis for n. Then for any x belonging to n, there exists unique scalars alpha 1, alpha 2 and so on alpha n such that x is equal to summation I is equal to 1 to n alpha I xi as above. Since t is linear, then t of x equal to summation I is equal to 1 to n alpha I t xi. Okay. Now, taking the norm of both sides, so norm of tx here, this is tx is equal to summation I is equal to 1 to n alpha I t xi. Then norm tx equal to norm of summation I is equal to 1 to n alpha I t xi. Okay. So here summation, if we take norm inside of summation, then we can write this is less or equal to summation I is equal to 1 to n norm of alpha I t xi. Okay. This is less or equal to summation I is equal to 1 to n norm alpha I t x I. Okay, and also we know that norm of alpha x equal to mod alpha norm x. Okay, so here norm tx less or equal to summation I is equal to 1 to n norm alpha I txi. So this can be written as mod alpha I norm txi. Okay, so here summation of this. So here n terms. Okay, mod alpha 1 norm tx1 plus mod alpha 2 norm tx2 plus and so on. Okay, suppose maximum of alpha I in each term. Okay, then less or equal to max of mod alpha I summation norm txi. Okay, so max alpha I is 0th norm of x, already defined here. Okay, so norm of tx less or equal to norm x under 0th norm into m, where m summation I is equal to 1 to n norm txi. Okay, since the basis is fixed, we can take m be constant. Okay, so it can be taken as constant m. Since all norms in finite dimensional space are equivalent, already we have proved, and T is bounded with respect to norm x0, it follows that T is bounded. Okay, hence T is continuous. So we know that if T is bounded, then T is continuous. So here T is continuous. This proves the theorem. Next corollary, any linear transformation between finite dimensional space is always continuous. Since the theorem is true for any arbitrary normed space n dash in above theorem, okay, here n dash is arbitrary and n is finite, then T is continuous. So here linear transformation between finite dimensional space. Okay, as per above theorem, since the theorem is true for any arbitrary normed space n dash, it is equally true for a finite dimensional space n dash also. Okay, so it is true for arbitrary, so it is true for finite dimensional space n dash also. Second, let T such that LPn to n dash, where P lies between 1 to infinity and n dash is any arbitrary normed linear space. Since LPn is finite dimensional, T is continuous by the theorem 2. Okay, this is like this theorem. Here LPn is n dimensional space or n dash arbitrary. So this is, and T mapping from LPn to n dash, here T is continuous also here. Hence T is continuous. Noting point, if n is infinite dimensional, the above theorem 2 is not necessarily true. In fact, we can prove the following theorem. Okay, theorem 2 states that if n is finite dimensional and n dash is arbitrary, then mapping T such that n to n dash is continuous. Okay, here n is infinite dimensional, then it is not true always that T is continuous. Theorem: let n and n dash be normed linear space over the same scalars. If n is infinite dimensional and n dash non-empty, suppose here n dash not a singleton set 0, that is n dash not empty, then there exists a linear transformation of n into n dash which is not continuous. Proof: let the basis for the infinite dimensional space n be ei such that I belongs to I, positive integer, with norm ei is equal to 1, okay, where ei is the unit vector, okay. Norm ei is equal to 1 for all I. Since n dash non-empty, it has a basis. Let it be fj such that j belonging to j also positive integer, with norm fj is equal to 1 for all j. Define a linear transformation T such that n to n dash as follows. Here linear transformation defined as this: let T of ei is equal to Fn for all I is equal to n, and T ei is equal to 0 for all I not equal to n. Then we show that T is unbounded transformation. Let x belongs to n. Then x is equal to a1 e1 plus a2 e2 plus and so on plus an en, where n is arbitrary. Since T is linear, we have, okay, Tx is equal to a1 T of e1 plus a2 T of e2 plus and so on an T of en equal to an T of en. Okay, why? Because T of ei is equal to Fn for all I is equal to n, and T ei is equal to 0 for all I not equal to n. Okay, so here at n terms, so Ten is Fn, okay, other 0, Te1, Te2 and so on, Ten minus 1 equal to 0. So we have Tx is equal to only this term an Ten, and Ten is Fn, that is Tx is equal to an Fn. But taking the norm this, so norm an Fn equal to norm of Tx, okay, and norm of Tx, that is this is less or equal to supremum of norm Tx upon norm x, where norm x is equal to 1. We can write, and as per the definition of bounded linear transformation, this is norm T. So norm an Fn less or equal to norm T. This is the norm an Fn, and we know that norm alpha x is equal to mod alpha norm x. Okay, so as per this definition, we can write mod alpha n norm Fn less or equal to norm T. Okay, Thus we have mod an less or equal to norm of t also. Since n is arbitrary, we conclude that t is unbounded. Here norm t greater or equal to mod an. That is, t is unbounded. So we know that t is unbounded, that is, t is not continuous. Therefore, there exists a linear transformation of n into n dash, which is not a continuous. In this lecture, we have discussed the further theorems on finite dimensional non-linear spaces. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Narisi. Second, function analysis with applications, John Valley, written by Erwin Krejcik. Third, function analysis, New Age International Publishers by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterrooding. Thank you.